Well, hello. We're getting down near the end of the semester, and before we dig into the topic today, note that on the last regularly scheduled class day, you have to do your have your project done and give a demonstration of it and give a report of it. The assignment specifics for that have been posted to the course site, so make sure to look at that and make sure to be prepared next Wednesday in class to talk about that. And this will probably be the last lecture because I want to leave next Monday open for you to work on your stuff. I may post a bonus lecture, but don't feel compelled to watch it unless it would directly help you with your project. But today, since there were a couple groups that mentioned making their game kind of network multiplayer playable, I'm going to at least give you a little bit of a quick start on how to do that with today's lecture. And essentially, what I'm going to cover today would allow you to set up kind of a game server that then the clients connect to and play that game over that network. And I'm going to kind of try to give you the foundation of how you would then expand that to do and send whatever data you need to have sent. So let's go ahead and dig into this. So first off, to make a multiplayer network game, we need to write our code in such a way that it can send data over the network. In other words, if you have two machines, think of one as the server, think of the other as the client. We need a way that they can exchange information. We need a way that information will go between those two machines. And the most universal way of doing that, at least at a low level, is to use what's called the sockets module. And sockets is a technology that the entire, almost every programming language supports some form of calls to the sockets library. And sockets is when you're watching this video on YouTube, there's sockets programming involved in allowing you to watch the video. When you're on Reddit and you're chatting with people, typing things in, viewing content, when you're on Discord and you're chatting with people, sharing files, it's sockets that's allowing that to happen. Now, the sockets module is really, you can think of it as a library or subsystem that allows you to do various kinds of network programming. So, and from our point of view, it's going to be what we're going to use to send data over an internet protocol, an IP-based network, which is entirely really what the internet is based upon, is some form of IP. Now, there are two ways to communicate over IP-based networks or over the internet. And there's what's called TCP and there's what's called UDP. And let's take a look at those two in a little more detail. So TCP versus UDP. TCP is Transport Control Protocol. UDP is Universal Datagram Protocol. And what's the difference between those? They both use IP datagrams to send things. The difference is TCP, you can think of it like a phone call. In other words, you make a call, somebody then answers, and at that point you are connected. And once you're connected, anything you say makes it to the other end. It's reliable. Anything that they say and respond back, you hear. Again, it's reliable. The sequencing is all guaranteed by TCP. It handles all that for us. But because it has to handle all that kind of streamed data and that sequencing, it can be, or it can have an overhead associated with it, because behind the scenes, if something's missing, it has to re-request it. If the re-request message gets lost, it has to wait and then time out, and then it has to send it again. And so there's stuff that happens behind the scenes that can make it fairly have a higher latency. And then for a real-time game, that translates to the game experience is going to feel sluggish and slow and unresponsive to a user. Now, on the other hand, UDP, you can think of that as more like mailing a letter. You put the data in an envelope, you toss it in the mail, and you go about your business. The problem with that is you don't know when they get it. You don't know if they got it unless they send a letter back saying, hey, I got your letter. And if any of those get lost, you don't have any way to know. But the advantage of those is because it's not doing any of that extra error checking and timeouts and making sure the other end got it and responding when you did and acknowledging things. It can be very fast and responsive, but it's unreliable. So you have this balance between reliability and guaranteed delivery and on the one hand, and on the other hand, something that's very fast and has low latency. So both TCP and UDP can use IDP IP to address and route the datagrams. They really are both just different ways of using the same technology. So let's take a look at both of them in just a little more detail here. So TCP, it manages those connections. It guarantees the delivery of a stream. It guarantees the reliability and the sequence order. In other words, if you send a message A, B, C, D, it's going to guarantee it's going to get delivered, and you're going to get it as A, B, C, D. It also will automatically divide a longer stream into smaller message datagrams to be sent in IP packets. So you might send a really large stream of data. You don't have to worry about how it gets divided up, how it gets put back together. TCP does all that for you. It can also automatically adjust to connection speeds, meaning that since it is stream-based, if you're just pushing data into there, it can tell you to slow down or speed up depending on the nature of the network and the congestion of the network and so forth. So data doesn't back up. It handles all of that automatically. And it's easy to use. You just say send, you give it some data, and on the other end you do receive, and it receives the data, and it does so reliably. But the disadvantage is that low or the high latency potentially associated with it, and the other disadvantage is, how do you know where one message ended and the next one begins if it's just a stream, unless you build in some kind of sort of dividing messages for yourself to receive those things on the other end. Now, UDP doesn't have connections. It's just datagrams. And a datagram, again, think of that like a letter. And there's no guarantee of delivery. There's no guarantee of sequence order. So if you send A, B, C, D, you could get A, C, B, D. And you can also get some things twice. You get A, B, B, D, C. So you could get them in a different order. Some things could be received twice. And some things might just get dropped. You send A, B, C, D. You might get A, B, B, D with no C in there. And so it's up to us to make sure that we receive that data and handle anything that gets dropped. Now, so there's no stream, just datagrams. Now, that there's an advantage to those being just datagrams, meaning that when you get a datagram, you get the letter, you know that that's its own separate message from the previous one. You don't have to build in some kind of separator in a stream. Now, another thing about them, datagrams, is your UDPs, there's no adjustment for connection speed, so we have to make sure that we're keeping up with the stream of data and build in our own way of saying slow down or hold on if we need to do that. We also have to handle any lost messages, any things that are delivered out of order, anything that's duplicated. We have to do that ourselves. And we should really add our own check value to the data that's being transmitted, since it's not necessarily guaranteeing reliability like TCP is. Now, given all of that, TCP seems like the easier choice. It does a lot of the work for us for guaranteeing delivery. You open a connection, any data you push in pops out the other end. But the problem is there are two problems with TCP. The first one is that TCP, since we're not sending a datagram, we just feed data into a stream, it'll kind of try to gather enough data until it has enough, and then it will send it out. Now, you can monkey around with those thresholds and make them so that they're lower. The easiest thing to do, though, if you don't want that, is to do a TCP no delay to set that attribute on your connection. And that means as soon as you give data, send data with send, it gets sent. It doesn't wait to kind of build up a group of data or a block of data. But that can make the overall process a little bit slower, but it can make things quicker. But even with that TCP no delay option set, TCP can still be slow because it automatically resends if something doesn't get acknowledged. Acknowledgement packets can get lost. Resend packets can get lost. And that delay latency could be a quarter second, 250 milliseconds for a resend. And it can be worse. If a resend packet is also lost, then we're up to a half second or maybe even 3/4 of a second. And notice that for a real-time game, like a first-person shooter, even that first quarter second, that 250 milliseconds, that's an eternity when you're dealing with something where people are using fast reflexes to take some action and decide what to do. And that can be a severe problem. So TCP can work for turn-based RPG, like role-playing games, or sending game assets like levels and textures and skins and sounds and stuff like that. TCP is great for that because it's reliable. It guarantees the delivery of whatever you put in there comes out the other end intact the same way it was sent. But it's not good for high-paced, really fast, low latency types of games like arcade games or something along the lines of multiplayer first-person shooters, or I guess side-scrolling shooters or something like that. But if for a turn-based game, I don't know if anybody's ever played a game like Worms World Party, where you take turns and you decide what action you want to take, and then it carries it out. TCP would be great for that. But it's terrible for real-time data because we, as the programmer, have no control over it. That's all done in the networking system, in the TCP libraries that handle all that stuff for us. Now, so for real-time multiplayer games, such as first-person shooters or real-time strategy games, something like UDP is really necessary. And why is that? Well, we want to lower the latency as much as possible, but that does mean that we're going to have to do something. So the idea is we want to have quick updates of inputs from players, server updates of the game state. Going to the client machines needs to be quick. The clients need to update that and render the screen, and you need to have that visual loop from you taking an action to seeing an event happen in the game on your screen. We need to have that be pretty quick. But because UDP is a simpler protocol and doesn't guarantee all that stuff for us, we need to think a few of those reliability things through and program around those shortcomings of UDP. Now, UDP, and this is more detail than you really probably need, but there is an important part of this that I want to mention here, that a UDP datagram is a lot simpler than a TCP datagram. And we're not going to worry about TCP datagrams right now because we're going to focus on UDP, because UDP is going to allow you to do some things that are high speed, low latency. And I think based on the games that were presented, that's the one that's more geared. But if you want to look up TCP, you can look at that. And really, even for using UDP, you probably don't care what the datagram looks like, but there's one important point here. Now, the first part is there's a source port and a destination port. The ports are kind of like extensions on your computer. That's how you can have your web browser with multiple tabs talking to different websites. At the same time, you have like a chat window open. At the same time, you have Zoom open. How does all that network traffic get sorted between the applications? Well, it uses port numbers to do that. And then there's a length here, and there's a 16-bit checksum, which is the check value. And then there's the payload. And you'll notice the payload, it says you can have a size up to 65,507 bytes of application data. And the reason it's that number, you have 65,535 minus 8 minus 20. That gets you down to 65,507. But we don't want to make datagrams that big, and there's a good reason for that. Large datagrams can be problematic, especially for game programming. And the reason is because IP will support, or TCP IP or UDP will support datagrams up to that 65,507 bytes. We want to keep it smaller, and the reason is because Ethernet, the underlying kind of networking system, whether it's Wi-Fi or a wired Ethernet, it really wasn't designed to handle datagrams that big. So when IP goes to send a datagram across a physical kind of network like Ethernet or Wi-Fi that does not support a datagram as big as the one it has to do what's called fragmenting it. And what fragmenting the datagram is, it's like, imagine you have a really large book and it needs to go into a mail system that can only handle letters. Well, the way you would fragment it is you'd tear those pages out, make individual smaller letters out of them. On the other end, when it gets them, it would say, look at the letter and say, oh, this is a book fragment. So I'll take those and I'll collect all of them. And then once I have all of them collected, then I will send that on as a book again. And notice UDP is doing that behind the scenes for us. But because it's unreliable, that can create problems. So here's an example of that happening. So the MTU, or maximum transmission unit, that's the size, the maximum size you can have, is right around 1,500 bytes. So if we have a, or is 1500 bytes, so if we have a 3000 byte UDP datagram that we want to send, it's going to end up looking like this. So here's the UDP header, and then here's the IP header, which is 20 bytes, so it's 28, and that leaves 1472 bytes left over. And actually, I think it's supposed to be 1476 there. Let me fix that real quick. Well, we'll leave it like this for now. But just know, I think that's 1476 is how big that's supposed to be. But you'll notice that with this, we have IP in the header. There's a flag that says if the more fragment flag, the MF flag is set to 1, that means that, hey, wait, there's another fragment coming. And if it's that one set to 1, it waits for another one coming. And if the last one is 0, it says, okay, now I'm done. Well, the problem is that each of these has an offset that tells how to fit those back together. Think of that like the page numbers on the book that we're using to collect it back together. But the problem is that if we have fragmentation, if any one of those fragments gets lost, because it's not guaranteed to be reliable, it has to discard the entire group of them. So if you think of like a packet that has, or a datagram that has 65,507 bytes, the largest you can have, that's going to end up as 45 IP packet fragments. And if just one of those gets lost, the whole message gets discarded. In other words, if it gets to the end and says, well, out of those 45, I had 44 of them or 43 of them, it doesn't have a mechanism to re-request the ones that were missing. It just says, throw the whole thing in the trash. So in other words, imagine this large book. We send all of the individual pages. It gets put back out on the other end, and it realizes there's a couple page numbers missing. It trashes the entire thing. And it doesn't tell anyone it did that. It kind of silently just fails. So we have no idea or no way of knowing that data was lost. So that can be a problem. So the solution to that in most real-time games is to try to avoid those large UDP datagrams. And if we keep our datagrams to a size that's below that maximum size, 1476 bytes maximum, if we keep it to that or below, then it's never going to get fragmented. So we need to be, I guess, aware of that and cognizant of that when we write our network code to not be sending large amounts of data, because it can lead to increased failures of those messages to get through. And also, the more data you're sending, the slower it is, the more you have to process. So it's a good idea to keep that small. Okay, so let's focus on using UDP. And why? Well, it's fast. And if we use datagrams that are less than that 1476, there's no fragmentation that happens. UDP can, however, still lose some of those datagrams, but the general idea of how we're going to write this is the server is going to be sending out, hey, here's the game state, here's the game state, here's the game state, here's the game state. And it's going to be the absolute state of the game, meaning here's where all the players are, here's where the bullets are, here's where the items are. And the idea there being that if one gets lost, there'll be another one that comes in shortly after that. So we don't really need to worry too much about if one gets lost, it gets lost. Now, on the client side, though, we might need to worry about that a little bit more, because if a event message gets lost, like a key down gets lost, then we aren't going to know that that was lost, and that can create a problem where we fired the gun, but the server didn't see us fire it. So we need to consider about how do we make that more reliable. Now, one thing to note, if you just need a reliable way to transfer files like textures and skins and things like that, you should use TCP, or consider using TCP and not UDP. Now, there is something that's important here, that if you're writing a large network game that's fairly complex, I've written code that uses both TCP and UDP together. It uses UDP for the real-time data, and then it uses TCP to load the assets at the beginning of a level or something like that. So consider the advantages and disadvantages of each. But we're going to focus on UDP since that seems to be more aligned with real-time interactive games. Okay, so let's look at how we do the UDP client programming first. So to perform client programming in UDP, the first thing we're going to need to use or to get a socket to communicate on is import the socket module. After that, we're going to create a socket object, and we do that by socket.socket, and then we pass in the two parameters AF underscore INET, socket.af underscore INET. That's the address family for the IP-based networks or internet. And then we're going to do sock underscore dgram. Sock underscore dgram is what makes this a UDP connection. If we did sock underscore stream, that would be a TCP connection. So the difference between creating a UDP connection or UDP socket and a TCP socket is just whether we put sock underscore dgram or sock underscore stream here. We're going to do sock underscore dgram. And then I'm going to set that client socket to non-blocking. And the reason for that is we don't want our game to stop generally. Maybe sometimes you do. But in most cases with a real-time game, if we're using UDP, we don't want to stop until it gets a network packet and then continue. We want to just say, if a network packet comes in, do something with it. Otherwise, keep rendering and drawing and having things happen in the game. The next thing we need is the client address or the address of the server we're going to be talking to. In this case, notice I'm putting the IP address 127.0.0.1. That's what's called the local host address. That's the address of the machine that we're on here. Now, if you were writing this to be a network game that was available over the internet, you would need to give this an address that was a static IP that was assigned to you to run that server on that this is going to talk to. Or if you're on a LAN game, you might put the address of the other machine that's in the room with you. You might ask them, hey, what's your IP address? They would run their server on that IP address. You would run, then put that address in here. But 127.0.0.1 is a special address that's reserved for local things happening on the local machine, not going out on the internet. And then this second number is the port. I just picked port 12,000. I picked that because port 12,000 used to be the what Quake servers would run on many years ago. But really, you can put any number you want there as long as it's not a port that's already in use by some other network application. I'll put 12,000 there. Now, but note that that address that we're putting in here and this port need to match the address and port that's on the server. Okay, but after we do that, if we make it past this line, we're now ready to send and receive UDP messages to and from this address. Okay, so here's an example of sending a message. We would say, I made this message string, hello Watson, with an exclamation mark. And what I did here is do message.encode UTF-8, that's 8 bits per byte. And the reason that we need that, you didn't used to need that in older versions of Python, but now strings are all Unicode strings behind the scenes, so we need to convert it to this 8 bits per byte UTF-8 encoding. You could also encode it using a thing called Latin, which will make it kind of a normal ASCII encoded string. But generally you use UTF-8 here. And so what we're saying is on the client socket, send this message to this address. And this is going to be the address of the server. So in other words, this is the address we're writing on the outside of the envelope. This is what we're putting inside the envelope, in this case, hello Watson. And on to receive data, we're going to do a client socket.receive from. So you do send to send, you do receive from to receive. This is the maximum we're allowing it to receive. And then when that comes in, we're going to get the message and we're going to get the address. And generally, since the socket was set to non-blocking, I'll put this in a try except block so that if this fails, the message will be set to none, the address will be set to none, rather than having it say, hey, I tried to receive data and there was nothing there, and having it crash your program. And because we turned off that blocking behavior, when there's no data available, receive from throws that exception. We're catching that and then putting none in there. So we catch the exception, report a message of none, report an address of none. So in other words, if I get something after this block of code and message is something other than none, I got a packet that came in, a datagram that came in from the other end. Now, for data encoding, notice back in this example here, we were just sending a string. But a better idea would be to have some way to encode game data, like you take a list that's in your game, a list of bullets, or a list of players, or a dictionary of something that's in your game. And to encode that, what I'm going to suggest we use is message pack, which we talked about a couple lectures ago when we talked about storing complex data in files. If you wanted to, you could also encode it using pickle. or JSON or struct. You could use struct.pack and struct.unpack. But I'm going to use message pack because I've used it before. It's very good to use for games. It's compact, it's fast, and it's also cross-language and cross-platform. So the idea there is if we use message pack, that's going to allow us to pretty much encode a very large number of types of objects. And here, what I'm going to put in there when I do that, I'm going to do a message pack.dumps. I'm just going to put in the game object there. Now we're going to modify that a little bit here when we look at some code, but we'll talk about that. So in other words, to encode the data and send it, we use message pack.dumps to encode it, and then we just send that message to that address. And when we receive a thing, we do client socket.receive from, and then we unpack it if we received it. So message pack.loads instead of dumps the message, and now we have that object back. So in other words, think of these two sets of code as here's a mechanism we can shove an object into. It'll travel across the network, and that object will pop out the other end. So if you had a list, you could stuff a list in there. A list will pop out the other end. If you have a dictionary, you stuff the dictionary in there. Dictionary pops out the other end. Now, that gives us a way to move an object from one machine to another machine, or from one program to another program that aren't necessarily running on the same machine. So here are some UDP client snippets here. Again, import socket, open the socket, create the socket object, set it so it doesn't block, create an address that you have the server that you're going to talk to. Encode the message, receive a message, and then if we have a message of something other than none, process it. And then we would write the code that processes that. And on the server side, it's pretty much the same sequence of things. We open the socket, or create a socket, set it to non-blocking, set its address. Notice here I put the double quotes there. That means use the default address for this. And then there's one other step. We have to bind the server socket to that address so it can receive things on that address. And then receiving works the same way, processing works the same way, and sending works the same way. Now, one thing to keep in mind is notice I switched the order around on the server, and that's so that when this one is sending, this one's receiving. And then down here, when this one is sending, that one's receiving. All right, so now we need a protocol. So the basic idea of protocols used for games generally work something like this. That we get input from the player on the client machine, and we need to send those input and control events from the client machine to the server. The server then is going to update the game state of where everybody is in the world and what their health is and who hit who and all that stuff. And then it's going to then send out that game state information to every client that's currently connected. The client will then receive that new game state data from the server. It'll update its local game state on the client in the client program, and then it will essentially render all of that on the screen, and it'll repeat that. In other words, get keyboard input and mouse input, send that across in some way to the server. The server updates everything and then says, hey, here's where everything is. Client draws it, and so forth. Now, the server is also going to need to have a way to have players join, a table of currently connected players and their addresses so it can send data out to each one. And it also is going to have a way for players to exit the game when they're done, or a way to quit the game, I guess. So both client messages and game state information does need to be encoded. And like we talked about in the previous lecture, you could use JSON, Pickle, XML, struct.pack, and so forth. We're using message pack because it's language independent, platform independent, fast, and compact. And you might ask, well, why have it be language independent? Well, you might want to write your server in a different language, or write the server in C to make it faster, or write the server in Java or something. So having it be language independent could be important. Or you might want to write the server in Python and the clients in C++ or C# or something like that. Okay, so here's what we're going to build. We're going to have a client game loop that's going to get user inputs put events, send them, put them in a UDP packet and send them. If data then arrives from the server, let me fix a typo in here. So if data arrives from the server, then we receive that game state packet, we process it to put all the game variables where they need to be from what the server told us, and then render it, and then repeat that over and over again. Get events, send the events to the server, get what the server says the game state is, render it, repeat. Now the game server side, it's going to receive client events. If a client joins, it adds them to the client table. If a client exits, it removes them from the table. And then it's going to process any other events that came in from clients, update the game state via simulation, and then at the end of that main loop, send out the current game state to all the clients that are currently playing the game. Now, there are a few potential problems here that we probably ought to consider, and those are that UDP is just sending the datagrams. So because it's UDP, it's unreliable. So that means that events that are sent from the client to the server could be lost or received in a different order than they were sent. Game state responses could be lost or received out of order. Different event types have to be sent maybe at the same time in the same packet. So in other words, they can press the mouse and the keyboard at the same time. Maybe have to have a way to send all of that. And the game state could be very large, so multiple fragments are needed. We're going to try to keep below that 1476 limit, though, so we don't have to worry about fragmentation. So we want those updates to be quick. So to start down a protocol, we need to figure out what messages need to be sent. And here's what I would suggest. From client to server, we need a way to send the events of the client, the player. What keys did they press? What keys did they release? Are they joining? Are they exiting? And a keep alive. Keep alive messages might be used to send periodically on a timed basis to say, hey, I'm still here, I'm still here, I'm still here. And that means that if they're not joining or exiting or pressing keys, you don't want the server to think that they're inactive and drop them. You want that to know that they're there. And a keep alive message doesn't really have any effect on the game, but it's a way to keep your client connected. And really, what I would suggest is rather than key down and key up, you maybe would have mouse events too, but I would suggest rather than key down and key up, you would have something along the lines of the keyboard state right now from the client. And that way, if a key down gets lost, you see it in the next message. Now, the server to client, we need a way to send all of the game state. And that might include the list of the players and where they are and what their healths are, maybe the bullet list of where all the bullets are and the direction they're traveling, maybe who fired that bullet, maybe item lists, maybe health box lists, maybe enemy lists. But there could be pretty much you're sending the list of all of the game objects that make up the game state. Now, keep in mind that those need to be encoded in some way, probably using message pack or something like that. And we need to, it'd be beneficial to us to keep the size down below that 1476 byte limit imposed by Ethernet. All right, so a couple things to consider. You want to plan for losing packets, plan for things that come in out of sequence, plan for lost or delayed game state packets, plan for out of sequence game state packets. You don't want to have a bullet moving and then jump backwards and then go forwards again. And plan for users dropping out of the game. That's what that keep alive message is for. And some packets might need to be acknowledged. Like, for example, when somebody goes to join, you might need to make sure that you send them a message saying, hey, I got your join message, and now you're ready to play the game. So that way they could try to join again if they didn't get that. All right, let's look at a little bit of code. The first code examples I'm going to look at, let me go ahead and bring those up, and then we'll take a look at those. And I'm not going to write this live because I want you to have plenty of time here to work on what you need to work on today. And let me switch this over so you can see what I'm doing. Okay, so here's a client. the client code, I'll bring that up first. I'll put it over here on the left. And if you notice with this client code, a couple things. Well, let's bring up the server code side by side with it. And I will post these to the course page, so don't worry about copying them down or retyping them or anything. At least not right now. All right, and here's some server code to go next to the client code. Put that right about there. Okay, first thing to notice is I'm importing socket, I'm importing message pack, and then other than that, I'm not doing much of anything. Also notice on the server side, I don't necessarily need Pygame. I don't need to import Pygame over here. Now what I've done here is I've created these abstractions with this UDP Client class and a UDP Server class. And the idea is that we have a send object and in both and a get object in both. So in other words, this is going to be what's going to allow us to send an item through. Now the cool thing about this implementation, the way that it's set up here, is what I did was I passed that item in, but I also give it a name. And giving it a name can be helpful for knowing what that data is when it comes out the other end. So in other words, I'm going to say send object. You might say send the key down event. And then you would pass the item that's the key, like keyboard key. Is it A, is it B, is it C, whatever key it is. Or you might say from the server to the client, you might say send an object, bullet list would be the name, like a string bullet list. And then you would put the actual item data here in there. And that would send that bullet list back to the client. Or it could be the GameState dictionary that we're plugging in here and sending that back. And then you'll notice, so we have a send object and a get object, or a put object and a get object, send object, receive object, whatever you want to call them. Now I kept this code really simple on purpose, and you'll notice what I'm doing. The only kind of thing that I'm sending is I first send a connect message, and I'm just sending the data client, so I'm just saying connect client. You might have the name of the player here, like player 1, player 2, whatever. So you might have a thing that asks them for their name, and they put their name in, and then when it connects, it has their name that shows up to keep track of that. And then down here, the only other things I'm sending is a message that's a key down event or a key up event. So if they pressed key down, I send that message that's in key underscore DN. If it's a key up, I send the message key underscore UP. And that's it. That's all I'm sending on here. I'm not rendering anything. I'm not really doing anything. I'm just doing that. Now, inside of our loop, though, we could call, notice I have some comments here. I said we could call netClient.getObject here. And if it was something other than none, then I could get the GameState, update all the variables to show whatever I'm showing on the screen. All right, let's go ahead and run this and see it at work. So on the server side, it's pretty much the same thing. I do have this player list and this bullet list thing down here. But those are not being sent right now. Here, let me scroll down so you can see. Wait, I need to shrink this window a little bit. Okay, so now you can see the bottom of that. But you'll notice that I can create this GameState dictionary. I can put the player list. I can put the bullet list in there. And we could actually then send that GameState down here. I'm not sending anything right now. I'm just doing a get object. And if the name is something other than none, then I print out the name and the item. Now we could take an action on that. But notice I kept this really as simple as possible down here. So let's go and run the server first. And it says server ready. And I'll put this over here with the server code. Let me shrink that down too. Okay, so there's the server code running there. Let's run the client. There's the client. And the client actually is a Pygame client. So let me shrink that down too and put it down here at the bottom. But one of the things you'll notice about that, when that connected, the server got the connect message. And it says where it came from. So now if I press a key over here, like A, you'll notice I pressed it and released it. Notice that the server got that key down A from this client, same one that's up there. So if I press A again, down, I release it, up, S down, S up. And you'll notice as I type here, you can see those messages coming in to the server and then getting printed there. And that includes things like space bar or digits or other characters. They just come through to the other end as soon as I press a key. That event comes through. Now, the cool thing about this is that of using this is we kind of have this abstraction here to send an object and receive an object. And we can just stick whatever object we want in there. Now, let's go back to our presentation for just a second here. All right, so we wrote our code. And now we're up to the point where we want to make a network client network server class. And to simplify some things to ourselves, we're going to make some classes that do some of the work for us. And so we want to make a pair of classes that open and manage the network socket, have a method to send Python objects, have a method to receive Python objects, have a way to add a label to the objects. Okay, we already did all that. That's what we had in the previous thing. And that's going to allow us to push those objects through with a label. We saw that with KD, KU event types, key down, key up event types, connect event types, and so forth. And we're going to use those to identify those objects that go out. So here's essentially what we created. You have a key down that's A. The name of the event type is key down. The item itself is the data A. We pass that through. It gets received. The server then knows, hey, that client, on their keyboard, the A went down. And then over here, we then change the GameState. We're going to send that back with the name GameState. So here comes the GameState object. Here's the actual data for it, and that comes back out. So we looked at that code already, but what I want to do is look at a protocol for something that actually plays a little more like a game. And let me just bring that code up and look at that. So I'm going to go back to my client and server here. So here's the client side. Here's the server. Let me open a different file for each of these. Let's do file open. And then I have a different example program here. Let's do client 3. And let me shrink this down. Oh, I need to make it so you can see what I'm doing. So I just opened a different program. And then I'm shrinking the window size down. And this program might seem quite a bit different than the previous one, but it's really not. It's the same things. Notice that we just have this player client, and then down here in my main loop, I'm sending the stuff. But notice I'm sending just key down and key up events again. But I also added the code here to say receive a message from the network, and if that message it comes through, as it comes through, I'm going to process it down here. And I'm not exactly using my named message system here. I probably should be, but I didn't. But I would use that named message concept previously. And now let me go and open the server code here. That goes with that. And let me shrink that down a little bit. Okay, so there's the server. And you'll notice the main difference here is that this is actually working more like a game. In other words, there's a little more code here. And what I'm doing is the GameState dictionary, I'm putting the player dictionary list into that. And on the other end, when I pull that out, I'm pulling out if you look in process message, process net message, I pull out the game or the player dictionary list and put it into that, and then I update the position of all the players there. So let's go and run this and see what it does. All right, so I think that I have the other program still running, so I need to get rid of that. So hold on just a second. Let me do that. All right, let's try again. Now notice that in this case, there's the server. And all right, so I apparently still have something running. So let me close out of everything except for. Okay, so there's the server. Server is running. And now let's run the client. There's the client running, and you'll notice that in this code I have this face that the client is now. So when those keyboard events go through, you'll notice them coming off the other end. So as I'm moving around, the server is tracking that. Now there's really no reason for the server to be drawing that other than that you can see it. And in fact, if I run another client and then connect to this, you'll be able to see them both. I'll move this one up to the top. Let me open another client program here. So here's another client instance. Let me run that one. There's that one. You notice that immediately that when it joined, there were two of those. Let me go back to that so you can see both of these. So there are the two screens. So if I move around in this one, you notice the character moves around in all three. And then this one, if I click down here to move around in it, the green one moves in the other ones as well. So this is essentially how you're going to be able to make something like a network game. And notice to extend this, it's pretty easy. That we just send different events through from the client to the server. The server then receives those events and does something about them. Could be spacebar to fire. Could be G to grab or D to drop an item or whatever you want it to be. This is only keeping track of the positions and sending those out, but then the server would update the game state and send the game state out. And notice since I sent that as a dictionary, it's easy to just stuff more things into there under keys and send all of them at once. So you could send in bullet list. Here's the bullet. Here's where all the bullets are. Item list. Here's where all the items are, and then render those bullets on this side and the items on this side. But hopefully that gives you a. Notice when I escape out of that, it exits from the server and it exits from that game. So if I escape from this one, notice now all the clients are gone. But the server is still running, so we could reconnect again with another client, and it would have them join that server with a game in progress. Okay, so hopefully by looking at that code, that will give you some ideas for how you would want to implement that. There's a whole lot more we could do with this game, network game stuff in here that we really don't have time to do today. And I want to be done in about 45 minutes, and we're already at 49 minutes. So, but I'm going to post this code to the course site. You can look at it, look it over, look at how it works, figure out how it works. There's some changes I would make to it to make it a little cleaner. But notice that the way this is written, it allows you to just put objects into that game state dictionary, as many as you want. Right now it's only putting in into the GameState dictionary, just this. But notice I have a comment there. Other things could be added to the GameState dictionary. Bullet list. So this is the player dictionary list. You could add the bullet lists or bullet dictionary list. You could add the item dictionary list, whatever. And when those pop out the other end, they pop out since message pack unpacks that dictionary. It pops out with the name that we put it in. So notice here's where we're putting it in. Here's where it's coming out, and now it's back to that dictionary, just like that dictionary jumped. The player dictionary jumped from one end to the other, one program to the other program. That's essentially what happened. We just use message pack to encode it, or we put it in the dictionary, use message pack to encode the dictionary, stripped out of the dictionary, use the key name to then put it back into this variable on the other end. So we kind of passed a variable from the server to the client. And then going the other way, we're doing the same thing when we send those messages down here. Send net message. Here's the key or the event string on the other end. We're decoding it and doing something with it on the other end. Okay, so let's go back to the presentation just for 1 second. We looked at that code. And again, feel free to use that code as a basis for what you're going to do for your project if you need to do that. And that's all for today. Everybody stay safe. Work on your projects. And again, be ready next week on Wednesday to present your final project and do a demonstration of it. And look at the assignment guide and make sure you understand what it is that you're being asked to present and what you need to do. If your program doesn't work, that's going to reflect badly. And I want you to think about this presentation as, think about it like a kind of presentation you would do for a investment group or investment board, or I don't know, like a game development conference where you're showing it off. Think of it, try to be professional. Try to demonstrate it in a way that's like, look at this thing we did, this is really cool, and show it working. If you get up in front of the class and you say, well, I didn't really get anything working and I didn't do anything, and the code I did write, it kind of sucks and it's dumb. I want you to try to sell us on the idea, and I'd rather have something that works that you can demonstrate a little bit than for you to just say, well, I don't have anything and nothing worked. So keep that in mind, that you should focus on getting something working, something demonstratable and playable. And if it's polished up, that's great. But polish on a car that doesn't run doesn't get you very far. But a car that runs, but you can say later on, I'm going to clean it all up and it's going to look great, and I'm going to add new upholstery and I'm going to give it a paint job. I'd rather see it run and do something and kind of embody the idea of the game than just be passive and sit there. But make sure to look at the assignment sheet, what's expected for you for the presentation and the submissions, and make sure to get those prepared for next week. If I do post another lecture next week, class 22 special topics lecture, it might be on making your code faster, since some of you might benefit from that. If I don't have the time to get that up, then this will be the last lecture, but no matter what, I'll see you Wednesday during the normal class time. All right, that's it. Thanks for watching. I'll see you guys shortly. And if you have questions or you're stuck, you have problems, shoot me an email, send me a text message. We can jump on a Zoom call. I can help you if you need it. That's it.